Thank you very much for the introduction and for the invitation. It's a great pleasure for me to talk in the conference. Let me briefly introduce the topic I'm going to talk. Maybe some of you are familiar with the private set intersection problem. Alice and Bob hold two sets of secrets from the same ground set, and they want to privately compute the intersection of their sets. That is, in such a way that nothing else is leaked about the other elements in their respective sets. In the basic formulation of the problem, we assume that they are honest but curious, which means that they follow the protocol but try to get as much information as possible. And to simplify the presentation of the protocol, let us assume that only Alice needs the result of the computation. Of course, PSI is a special case of secure two-party computation, so general solutions could be applied. But the specific structure of the problem has enabled, along the years, the realization of several custom protocols. Why? Because plenty of applications can benefit from efficient solutions to the PSI protocol. Let me just consider one of these applications to give you an idea. Let us consider private contact discovery. Perhaps all of us are familiar with this problem. When we use a new messaging app, we would like to know which of our contacts use the same app. One possibility is to ask the server and getting back the identities of our contacts, but in such a way, we are giving too much information to the server. It would be really nice to avoid such a leakage. On this slide, I have just reported the majority of papers which have been presented since the introduction of the problem until nowadays. And as you can see, more or less, the number of papers per year is more or less the same, which means that the interest has been constant along the years. And we can say that at the moment, PSI is a solid research area in secure computation. What we would like to do is to get some answers to this question. What about privately computing functions of the intersection? So the setting is the same, but Alice and Bob, in this case, want to privately compute a certain function of the intersection in such a way that nothing is leaked about the intersection and, of course, the other elements in the sets. Of course, also this problem is a two-party computation problem and can be solved with the general solution. But since we have seen that for the intersection, we have efficient custom solutions better than the general solution, we have the following questions. Can we get also for specific functions of the intersection more efficient solutions? And if we can we perhaps modify the protocols for computing the intersection in order to compute specific functions? Or if we cannot, can we at least borrow some of the techniques for computing the intersection? And from a more abstract point of view, which functions are suitable for an efficient computation by means of custom protocols, and which one are difficult? So, what I'm going to discuss in this talk in the remaining time is the following. First of all, I would like to give you just some ideas of the techniques which have been used in the design of PSI protocol. And I'm going also to point out that some functions of the intersection can be easily computed by modifying these protocols. On the other hand, I will point out that some other functions are or seems at the moment difficult to compute, or at least non-trivial at all. And I'm going to close the presentation, if I have time, by giving just an outline of a hybrid solution, where by hybrid I mean half custom and half which uses the general solutions for the computation of some specific functions. So let's go. The simplest way for computing the intersection is the following. Assume that Alice and Bob possess a cryptographic hash function. Bob can hash all the elements in his set and sends the hashes to Alice. Alice can do the same and can compute the intersection of the hashes, taking the corresponding xi. Notice that computing the intersection of two sets in clear from an algorithmic point of view is an efficient operation. The problem is that that solution is not secure, in the sense that if the ground set U is small, Alice can evaluate the hash function wherever she likes, and so she can get information about Bob's secret. And even if the set is not small, but the distributions through which the secrets are drawn have low entropy, think about the telephone number I was talking before, the attack applies. So we need something else. But it's surprising, in many settings where private set intersection protocols are used, such a solution is still present. A nice and secure way to do private set intersection is by using the Diffie-Hellman key exchange. In this case, H is a function which maps the element of the ground set in a properly chosen group. And as in the Diffie-Hellman key exchange, Alice chooses a private exponent A, rises to the power A the elements of the group she has obtained, and sends these elements to Bob. Bob does the same by choosing a private exponent, and then Bob computes and sends also the Diffie-Hellman elements. At this point, Alice, by using the element of the second rows, can compute by herself the Diffie-Hellman elements and can compute the intersection of the Diffie-Hellman sets of elements, taking the correspondent xi. Such a protocol, by properly choosing the group and under well-known assumption, is a secure solution and is also efficient from a communication point of view. Another technique which has been involved along the years leverages on encryption schemes with special properties. For example, an additively homomorphic encryption scheme is an encryption scheme in which, given the encryption of two messages, M1 and M2, it's easy to compute an encryption of the sum by working only on the encryptions, of course. And it's also easy to compute an encryption of a certain constant for the message. In a fully homomorphic encryption scheme, roughly speaking, we can do both operations by working only on the encryption. We can compute also the encryption of the product of the two messages. With these tools, we can work on the PSI area as follows. So, the first protocol works in this way. Alice embeds in a polynomial as roots of the polynomial the secrets of her set and sends an encryption of the coefficients. Bob noticed that from the encryptions of the coefficients can evaluate in encrypted form the polynomial p in each point of his sets. And this is basically what Bob is going to do, because chooses some randomizing elements and computes these encryptions, which sends back to Alice. Let us look at the first one, for example, at U1. you can see that if y1 is a root of the polynomials, the first part of this encryption is 0, and the second one is exactly the element of its set. So, what Alice has to do is simply to decrypt, and she gets random values in correspondence of elements which are not in the intersection, but gets exactly the yj for elements which are in the intersection. More or less along a similar path, by using a fully homomorphic encryption scheme, Alice can directly encrypt the secrets and send these encryptions to Bob, and Bob can do the following: chooses some randomizing elements and computes this encryption. Let us again look at the first one. The first one is an encryption of the polynomial which you see on the bottom of the slide. And it's not difficult to see that this polynomial evaluates to 0 when one of its secrets is exactly equal to x1, which means that Alice, by decrypting the elements, gets 0 in correspondence of the elements which are in the intersection. Another technique that has also been used for computing private set intersection is the OPRF. A PRF is a pseudo-random function, that is a function which is indistinguishable from a truly random function to any efficient observer. An oblivious PRF is a protocol for obliviously computing the pseudo-random function. Let us look at the example. Bob has a key, Alice a point on which she wants the value of the pseudo-random function. Through the protocol, Alice gets the point and Bob gets nothing. Actually, in the literature, in several protocols, such an idea has been implemented in a one-time fashion. Alice is the only one that provides an input, and as output, Bob gets a randomly chosen key, and Alice gets the evaluation of the function on the points, on the point. How it can be used? Bob can choose a key. Alice and Bob can run the OPRF on the first element of Alice's set. They can do the same for all elements in Alice's set. And finally, Bob can compute on all the elements of his sets the pseudorandom function, sending the corresponding pseudorandom values. At this point, Alice can immediately compute the intersection on the pseudorandom values and can take the corresponding xi. Actually, such a tool has been used in the literature to get more efficient solutions by using some data structures like Bloom filter, garbled Bloom filter, or hashing techniques like simple hashing and Cuckoo hashing. And the key tool which has been used in these protocols also for implementing the OPRF is the oblivious transfer. Unfortunately, I have no time for details on these tools, on OT, the beautiful concept of OT extensions, on random oblivious transfer and so on. But let me just point out that with this approach, we have the most efficient custom protocols for PSI known at the moment. Summarizing, what we have seen is that all protocols more or less use some pseudorandom representation of the secrets. An equality test is used for finding the matches, and data structures are used more or less to reduce the number of equality tests. And just to give you an idea of the performance, As you can see, depending on what we are interested in, runtime or communication complexity, the solutions I have described have a different behavior. And it's also interesting to point out that the naive solution, which is the simple lashing, is not secure, but performs, of course, better than all the others. So, what can we say about computing functions of the intersection? We would like to emulate this ideal world in which Alice and Bob inputs the sets and Alice gets back only the result of the evaluation of the function. Some functions are easy to compute. For example, let us assume that Alice is also only interested in the cardinality of the intersection. By using the Diffie-Hellman protocol I have described before, all they need to do is the following. At each step, they need to randomly permute the elements that they send to each other. Why? Because maybe it's not immediate, but Alice can still compute the matches, but cannot relate to the elements of her set anymore. So she can just count the matches. So that's easy to do. Let's consider another function. Assume that x and y, the two subsets, are ordered. They are just numbers, for example, and Alice would like to compute the minimum of the intersection. An idea could be the following. Alice, by using the Diffie-Hellman protocol, sends only the first element in order to check if it's the minimum, and Bob does what has to be done. Alice checks if there is a match, x1 is the minimum, otherwise she can repeat with another element. Of course, apart the merits that such a solution could have, it seems working, but if you think for a while about it, if such a protocol succeeds at the height iteration, well, Bob knows that in Alice's set, there are I minus 1 elements which are smaller than the minimum of the intersection. Maybe it's not a big problem, but we are not emulating the ideal world. The same idea can be applied for other functions. The protocol I have used the Diffie-Hellman type, but we can use also other ideas I have described before. In general, the serialization does not work. We can also think to some other approaches, like, for example, going back to another idea on the Diffie-Hellman protocol. Alice and Bob could work in this way. The first elements that they send to each other are not permuted. Bob just permutes the Diffie-Hellman elements he has computed. Also, this is not immediate to see, but what happens in this case is that Alice cannot compute the intersection, but can compute the positions in which of Bob's set in which they have common elements. So, with an extra message, Alice could say, please send me the element in the smallest position. But of course, also in this case, by counting the positions in the Y set, Alice is computing the cardinality. So this function seems to be at least difficult at the first trial to get. We could use the general solution. Let me say that along the years, what has happened? The circuit-based solution have been optimized for computing the PSI protocol. So we can use some of these protocols and modify the right one in order to compute the function we are interested in, or for some function we could compute ad hoc suitable circuits for the functions we are interested in. But this is a circuit design problem, so I'm not going to tell to tell more about that. What I would like instead to point out, and that's the last part and the contribution, the first contribution to this research project, is the following. There are some techniques which can be employed in order to design a protocol in which the first part is custom and the second part uses a small circuit. The technique I'm talking about was used some years ago in order to compute two functions of the intersection, which are cardinality threshold and cardinality range. Maybe basically with the first, the function gives 1 if the cardinality is greater than a threshold, in the second if the cardinality is between two thresholds. It seems to us that also for computing the minimum, the maximum, and the other statistics, this technique works. And it can also be applied to the other protocol I have briefly described, which is based on fully homomorphic encryption. And the key idea is that actually such a technique produces an intermediate pseudorandom representation of the intersection. Let's look at the first one. So here we are using an additively homomorphic encryption scheme. What Bob does compared to the protocol I described before is that this time he chooses some random elements which are representative of the elements in his set and computes the following encryptions, which are sent back to Alice. At this point, notice that Alice cannot compute anymore the intersection, but in correspondence of the element in the intersection, Alice gets the random value that Bob has chosen. And so at this point, if we are interested, for example, in computing the minimum, all we need is a small circuit like this. This is just a toy example, in which the circuit has given in output just the element for which there is the first match, and for all the others we just need to get 0, so no information. And the nice thing is that such an idea applies also to the other protocol, which uses fully homomorphic encryption. Why? Because also in this case, in a similar way, Bob can choose random values. This time, notice that the values are just n, 1 for each encryption that he receives. And as before, can compute such encryptions and send them back to Alice. And as before, what is going to happen? Also for this protocol, Alice does not compute the intersection this time. She does not get 0 anymore. She gets always a random value, but they get the same random values for the elements which are into the intersection. So by using the same circuit I've described before, they can compute the function of interest. And let me just point out that such a protocol was introduced some years ago for the unbalanced setting in which Alice has a small set and Bob a big one. And in this case, the circuital part we need to add for computing the statistics does depend only on the size of Alice set. So it's going to be quite efficient. Summarizing, as you have seen, I have many questions, but at the moment, few answers. For sure, we can say that the custom protocol for PSI seems difficult to adapt for computing other functions, but some of them, like the cardinality threshold, recently the intersection sum for an important application, can be computed. Then I've showed you this idea of a sort of hybrid construction. Well, what we need is a sort of experimental evaluation in order to quantify the benefits, especially compared to direct circuit-based protocols. For example, protocols starting from what is at the moment the state of art, which is a circuit-based protocol from a couple of years ago. In any case, custom protocols for some classes of functions, like for example statistics, seems to be an interesting mathematical and also practical challenge. And more or less that's what I wanted to say. Thank you for your attention. Actually, I have to say something more, and something more is happy birthday, Doug, from me and from all your friends from Salerno, hoping to meet each other soon again. Thank you.